and welcome back to Introduction to Astronomy. So if you are one of my students, I'm pretty much finished with lesson number 5. And so if you want, you can go to lesson number 6. Not yet, right? But you could go to lesson number 6. Now, for those of you who love mathematics, and who doesn't, everybody raise your hand if you love mathematics, okay? But if you like mathematics, I thought that you might find it kind of interesting to see where some of these formulas come from. So the first one is the tidal force. And the way that we derive the tidal force is that we imagine that the moon is actually made up of, we're going to calculate the distance from one side of the Earth to the moon, and then we're going to calculate the amount of gravitational force that one side of the Earth feels, and then we're going to calculate the gravitational force that the other side of the Earth feels, and then we're going to subtract those two numbers. And then that difference in the forces is going to be what's going to pull the water out on either side. So if you want to just do some of the algebra on that to prove that that really is how you get that formula. Now you need to remember that A is going to be much smaller than what R is. So you need to make an approximation which, well, if you've taken algebra, you know what I'm talking about. But anyway, that's where that comes from. Okay, another formula that we talked about was the Roche limit, and that was how close could a moon get to a planet without being ripped apart. So all we have to do this time is we're going to set the gravitational force that's going to hold two halves of the moon together. So we're going to take our moon and we're going to divide it into two pieces. So this one has a mass, this one has a mass, there's a distance between them, so there's a gravitational force that's holding the two halves of the moon together. Okay, but there's also the gravity of the planet that's pulling on this half over here, and the gravity of the planet that's pulling on this half over here. So that if we set those two forces equal to each other, the tidal force, and we're going to set that equal to the force that's holding the moon together, we'll find that at a certain distance, the tidal force will become greater than the force holding this together, and then it's going to pull it apart. And so if you do the mathematics, you end up with that formula there. Okay, another one was, do you remember that I talked about circular speed? The speed something has to have in order to go in a circular orbit around an object, and then there was the escape speed. So the way that we derive the circular speed is we set the gravitational force equal to another force called the centripetal force. So the centripetal force is when an object is going around at a certain radius and it has a certain speed v, it's going to feel this force that is going to be trying to pull it in, and then that's the reason why it goes around in a circle. See, objects want to go in straight lines because of Newton's first law of motion. So the force that causes something to curve instead of going in a straight line is going to be this thing that we're going to call the centripetal force. So we're going to set those two forces equal to each other, and we get that force that's called the circular speed equation. Now to find the escape speed, do you remember we were talking about energy, kinetic energy and potential energy, and which one was winning? So if the kinetic energy won, it would escape. If the potential energy won, which was caused by gravity, it would have a regular elliptical orbit. So all we got to do is set the kinetic energy, which is 1/2 mv squared, equal to the gravitational potential energy, and then solve it for the letter V, and you get that formula. And do you see how similar the two formulas are? So they're the same formulas, except that the escape velocity has an extra 2 inside of it. Are you still with me? I hope you haven't left yet. Okay, this is good stuff. It really is. And then here's one where we're going to calculate the total energy that the Earth has as it goes around the sun. So I looked up on the internet and I found out what's the speed of the Earth as it goes around the sun. And then I looked up and I found out how far away is the Earth from the sun. And so I calculated the kinetic energy of the Earth, 1/2 mv squared, and I calculated, I have a lot of time on my hands, I'm sorry. And then I calculated the potential energy of the Earth, and then I added them together, and do you notice you end up with a negative number? What does that mean? Gravity is winning, and that means that the Earth cannot escape because it's a negative number. Now let's compare that to Voyager. So Voyager is a space probe that we launched a long time ago, and is currently leaving the solar system. So I know what the speed of Voyager is. I looked it up on the internet, and I looked up the distance it currently is from the sun, and then I plugged all that information in, and I found out that its total energy, kinetic plus potential, is a positive number. What does that mean? It means it's escaping. So it's currently escaping the solar system. Where is it going? Well, in the future, it's actually on a collision course with a black hole. So it's going to enter that black hole. It's going to be spat out on the other side of the galaxy, where it's going to be adopted by an alien race of machines. And then they're going to build a gigantic spaceship around it, and they're going to send it back to Earth so that in 200 years, only Captain Kirk and the Enterprise are going to be able to stop it in Star Trek, the motion picture. It's true. So that's what's going to happen. Okay. So in our next segment, I want to continue, and I want to talk a little bit about precession, and then we're going to do our quiz.